Today we'll take a deep look into the distant future and see what actually awaits our solar system. In the Universe Sandbox simulator, I'll carefully simulate and model the events 1 billion years from now, then 2.5 billion years, and then we'll go even further to the era when the Sun eventually begins its transformation into a subgiant, swells to the red giant stage, and finally concludes its long stellar evolution as a white dwarf. Before we start, I want to thank my subscriber for providing the calculations and characteristics of the Sun for the required time intervals and each stage of its evolution, from the main sequence to the final stages. It's important to clarify, in this experiment, I won't take into account the orbits of moons around planets, their possible entry into the Roche limit, and other local processes. The main focus is on the changes to the Sun itself, its luminosity, radius, and mass, as well as how this will affect the orbits of the planets and their climate. In addition, I'll be reading out key information about the stages of the Sun's evolution, so that you better understand exactly what is happening at each stage. And let's start with the first scenario. Let's see what the solar system will be like in 1 billion years. As the Sun gradually consumes its hydrogen fuel reserves, it becomes hotter and hotter, and its luminosity slowly but steadily increases. By the age of 5.6 billion years, 1 billion years from the present time, our own daytime star will be approximately 15% brighter than it is now. I think you've noticed how the habitable zone has changed after 1 billion years. In 1 billion years, the age of the Sun will be approximately 5.6 billion years. The Sun will still be in the main sequence stage. Its mass will remain unchanged, the radius will increase by 10%, the surface temperature will be close to 5,900 Kelvin, and the Sun will become 15% brighter. After fast-forwarding a fair amount of time, the climate on Earth has stabilized, and as a result, the average temperature on Earth is 28 degrees Celsius, and the maximum temperature is almost 53 degrees. I'm hiding the atmosphere in clouds. As we can see, life on Earth hasn't disappeared. Yes, it's gotten warmer, seriously warmer, and we see that it's even flooded here, and it seems like there are more desert regions on Earth, but overall, the picture remains the same. There is life, and everything is fine. The polar caps have melted a bit, but the temperature there still remains below zero. It's the same in Antarctica. This is based on this simulator, and the likelihood of life, as we can see, has decreased quite a bit, and it's already at 80%. But if you look at habitability, Earth is already starting to enter the red zone a little bit. It's right on the edge, while Mars doesn't seem to have warmed up at all. It's just as cold as it was. And as for the objects further out, I think there's no point in looking at them in this case either. In the second experiment, we'll move even further forward in time and model what the solar system will be like in 2.5 billion years, when the Sun will be noticeably brighter and conditions on the planets will start to change quite radically. In 2.5 billion years, the age of the Sun will be approximately 7.1 billion years. This is still the main sequence stage. In this case, we see that Earth is already on the edge of the red zone, while Mars, on the contrary, falls into the middle of the green habitable zone. For such a Sun, the mass won't change, but the radius will already increase by 20%. The surface temperature will be approximately 5,950 kelvins, and the Sun's brightness will increase by 50%. I've fast-forwarded time, and here is what Earth has turned into. We see essentially a desert-scorched world, but there's still an ocean and liquid water. The average temperature is 55 degrees Celsius, and the maximum temperature is 81 degrees. The likelihood of life on such an Earth has dropped to 69%, meaning life hasn't completely disappeared yet. Let's take a closer look. I'll hide the atmosphere, the clouds. And we see that yes, there is life near the poles here. We see life in Europe, though vast regions are flooded due to melting glaciers. But along the equator, in Africa, there's absolutely no vegetation or life at all. In South America too, we see there's no life at all. Antarctica is melting, and the Arctic is melting even more actively. Vegetation is only in the northern hemisphere because we see that it's winter here right now, and little sunlight reaches this part of the planet, so the temperatures there remain more or less comfortable. As you can see, the simulator modeled it so that life on Earth still persists in this case, but only closer to the poles. But as I recall, life should disappear from Earth even sooner than in 2.5 billion years. Write your opinion about this in the comments. On Venus, I see it's only gotten a bit hotter. Mars has also warmed up quite a bit, but there's still frost everywhere, as we see across the whole planet. And I'll also show you Jupiter's moon Ganymede, and we see that it's warmed up quite a bit. The average temperature is minus 120 degrees Celsius. It was significantly colder before all this. And on Callisto, it's warmed up even more. The average temperature is minus 90 degrees Celsius. And here I am, right now, near Saturn's moon Titan. If we hide the thick atmosphere and clouds, we can see that its liquid methane lakes have simply vanished, and its average temperature has risen to minus 163 degrees Celsius. So, roughly speaking, the temperature rose by about 20 degrees, and that was quite enough for these liquid methane lakes to disappear entirely. As for the other moons, I checked them as well, and absolutely nothing has changed there. When the hydrogen in the sun's core starts running out, its outer layers will expand, and because of that, luminosity will increase while the temperature will drop. At the end of this phase, the sun will eventually transform into a subgiant. Next, we are going to look 4.25 billion years ahead. By that time, the total age of the sun will be about 8.85 billion years. This will already be the subgiant stage. As you can see, in this case, Earth is already completely in the star's red zone, while Mars is right on the edge of the green habitable zone, especially at its closest orbital point. When the sun is a subgiant, its radius will increase by 90%. The surface temperature will be about 5,500 kelvins, and the brightness will increase 2.5 times. I fast forwarded time, and this is what our Earth has become. The average temperature is already 180 degrees Celsius, and the maximum at the equator is 215 degrees. Life's probability on such an Earth has dropped to just 1.5%. Cloud cover hides the atmosphere. Wow, that's epic. The northern hemisphere is completely flooded. There's absolutely nothing left here. In Antarctica, we see only the ice is gone. The continent itself is still there. It's not flooded. At the equator, it's all desert, but at least it's not flooded. And this dense atmosphere we see on Earth formed from water vapor, and it's already 71 Earth atmospheres, and there's even some liquid carbon dioxide somewhere on Earth. The pressure on such an Earth is almost like on Venus, reaching 71 atmospheres. And there's a massive greenhouse effect, 144 degrees Celsius. Now we can safely say that Earth has lost its life. On Venus, the average temperature has also risen to 613 degrees, and we see that Venus is actively losing its atmosphere. Just a huge cloud of gases is coming off of it. If we hide the atmosphere and clouds, we see that Venus's surface has melted even more. Mercury's appearance hasn't changed much, but it's hotter, with an average temperature of 262 degrees Celsius. Mars has also warmed up quite significantly. The average temperature is now minus 19 degrees Celsius, and the maximum temperature at the equator is around 26 degrees. The atmosphere here is still quite thin, I see, but there is a very slim chance of life, 0.13%, and the surface pressure currently shows 0.02 atmospheres. Yes, the atmosphere got a bit denser, but it is still very thin indeed. Let's take a closer look at the surface. We see many icy patches have appeared on Mars. We see liquid water in certain areas of Mars. There's water here and there's water there. It's closer to the equator where Mars heats up most, though even here near the northern hemisphere there are some small bodies of water, and we see ice here too. Well, even though it's warmer, life can't form here due to the thin atmosphere, and there's no magnetic field. Now for Jupiter's moons. On Io, I see the temperature doesn't want to rise at all. On Europa, as we can see, nothing is changing temperature-wise either, but Ganymede has warmed up and the average temperature is already minus 94 degrees Celsius. And Callisto really surprised me. Look at its appearance. It has acquired a dense atmosphere. True, the average temperature here is minus 34 degrees Celsius, and it shows freezing temperatures all over the moon. But I opened the atmospheric parameters and there's a lot of ammonia, over 1 Earth atmosphere, lots of water, 195 Earth atmospheres, plenty of carbon dioxide, and sulfur dioxide is almost 1 Earth atmosphere. Wow. There's also a liquid ocean of sulfur dioxide, carbon dioxide, and ammonia. I wonder what's on the surface under those thick clouds, hiding the atmosphere and clouds. And wow, what do we see, guys? We see liquid sulfur dioxide, I assume. There it is, in red. And as is always the case in this simulator, if there's red liquid sulfur dioxide, then there will definitely be areas with greenery nearby. Well, look right there, there's green. In Universe Sandbox, I gather this is some kind of exotic life forming when liquid sulfur dioxide is present. Even in the southern hemisphere, it's the same thing. We'll see what happens to it after more time passes. By the way, the pressure is 1.87 atmospheres on Callisto, and the chance of life is over 7%. Not bad. Now for Saturn's moons, I checked Enceladus. Nothing special there, but Titan has some changes. It's warmed up here, and the average temperature is now minus 127 degrees Celsius. I'm hiding the atmosphere and the clouds. Let's see what has changed here on the surface. Well, we can see that not much has really changed. Now let's jump 5.5 billion years into the future, to the era when the sun will become a red giant and radically change the face of the solar system. After the subgiant stage, the sun's core will heat up so much that it will trigger hydrogen burning in the shell surrounding it. This will lead to a rapid expansion of the star's outer layers, and the sun will become a red giant. During this phase, the sun's radius will increase significantly. The star's expansion will lead to a massive increase in its luminosity and the cooling of its surface. In 5.5 billion years, the sun's Earth's age will be approximately 10.1 billion years. This will be the red giant stage, an RGB star on the red giant branch. But during the red giant stage, the sun will actively begin to lose its mass. I'm going to demonstrate that for you now. Let's start with the mass. And now using this slider, I'll start decreasing the mass. I'll decrease it bit by bit. In the meantime, watch the orbits and how they change. The planetary orbits should gradually start moving away from the star because the star's mass is dropping, and the planets shift to more distant orbits. So, I'm continuing to decrease it further and further. During the red giant stage, the sun's mass will drop to about 0.77 of its current mass. We can see how the orbits have changed like this. Not only are they further from the sun, but their eccentricity has also increased. Mars's orbit, on the contrary, seems to have become a bit more circular. I've opened Earth's characteristics, and we see the distance to the star is now over 1 astronomical unit. And here's Earth at its closest point to the star, where the distance is only 1.19 astronomical units. So Earth has really moved further away. It's the same with Venus. As we can see, its distance from the sun has increased. I've only changed the mass so far, but the sun's radius will of course grow. During the red giant stage, it will become enormous. Anyway, watch how all of this is about to happen. I am now beginning to increase the sun's radius, and it is expected to expand to about 165 times its current original size. Now, watch as this process unfolds. The star keeps growing, and then, bam, it swallows Mercury. That's not all though. The star will expand even further. We need to bring the value up to 165 solar radii. And there we go, 166 solar radii. I'll leave it at that. The star has begun to cool down rapidly. That's not right. The temperature of such a star should be around 3100 Kelvin. Look how it changed color instantly, and the sun will become incredibly bright, up to 2350 times more. We see that in this case, only Mercury was swallowed up. Venus is still surviving for now, but it's very close to the star. Earth continues to orbit, but there might be issues for it during later stages. You can see the habitable zone during the red giant stage. As we can see, even Neptune is now located within the red zone. I fast-forwarded time. Can you guess which planet is in front of you? If you said Earth, you're right, this is Earth. Earth has completely melted, lost its atmosphere, and has simply turned into an incredibly scorched world. We see that Earth is losing its matter. Particles are breaking away, they're just flying off Earth. The average temperature on such an Earth is over 1100 degrees Celsius, and the maximum temperature reaches over 1300 degrees. And here we see such a huge sun right next to the Earth. I've descended to the Earth's surface, and this is how that huge star looks in the sky from our planet. Also, from the Earth's surface, we can see its hot satellite, the Moon. It also looks roughly the same as the Earth. From here, you can see our Earth. Wow, look at that. On the Moon, the average temperature is 1207 degrees Celsius. Now you see Venus, it is extremely hot. The average temperature is 3500 degrees Celsius. But one thing is unclear. The simulator shows a thick carbon dioxide atmosphere, 53 times Earth's atmosphere. Could an atmosphere even still exist here? Maybe not enough time has passed for it to evaporate, but we see active evaporation of substances. I'll reset it to 0 to make it realistic, basically. And I think this version of Venus is more truthful at this red giant stage. After fast-forwarding time, the average temperature on Venus settled at 753 degrees, while the maximum temperature at the equator is 1413 degrees Celsius. And Venus, you can see for yourselves how close it is to the star. Just extremely close. Now you see Mars. Its average temperature is 951 degrees Celsius, and like Earth and Venus, it's losing its matter. The planet is simply evaporating. The star is just so close. Now for Jupiter's moons, starting with Io. Io has changed, it's gained this orange atmosphere, but the average temperature on it is almost 300 degrees Celsius. It's become very hot, but we see there's a minimum temperature somewhere, and it's freezing there. By hiding the atmosphere and clouds, Io's surface seems mostly unchanged, but right at the pole, there appears to be a small amount of what looks like some kind of liquid. Let's take a look at the southern hemisphere too. No, there's nothing here. Regarding that liquid, we can see it is sulfur dioxide, and there is very little of it, while the atmosphere itself is formed solely from sulfur dioxide. I don't see any noticeable changes on Europa, except that it has now warmed up to an average temperature of 262 degrees. No atmosphere has formed, and I take it all the water that was on the surface has evaporated, right? Now Ganymede, as we can see, it has no atmosphere, and the average temperature is 351 degrees Celsius. And Callisto, I knew it would be more interesting. Look at it. Yes, there's an atmosphere we see, but it's active actively losing its matter. Perhaps the atmosphere is simply evaporating. On Callisto, the average temperature is 375 degrees Celsius, but there's a minimum temperature of minus 24 degrees, hiding the cloud atmosphere. And we see there's no liquid on the entire surface, only a small amount of sulfur dioxide liquid at the northern pole. The color makes it clear. It's something similar to what's on Io. I've descended to Callisto's surface, and the atmosphere is so thick you can't see the star at all. That's how it all looks. Basically, you can't see a thing. And the gas giant Jupiter itself has heated up to an average temperature of 344 degrees Celsius. Now you see Saturn. Its average temperature is 266 degrees. Now you see Enceladus, a moon of Saturn. Its average temperature is 171 degrees Celsius, and this moon turned out quite interesting in this simulation. A small atmosphere of water vapor has formed on it, and it also shows liquid water in some places, but there's very little of it. Hiding the atmosphere and clouds, let's try to find it. And here it is, this liquid water, and there's actually quite a lot of it here. Look at that. Enceladus surprised us, but obviously there is no life here. Titan's situation is worse. It completely lost the atmosphere it once had, and the average temperature is 274 degrees Celsius. But look at how Uranus has changed. It's no longer that pale blue it used to be, but just green. It's become more beautiful, I guess. The average temperature on it is 73 degrees Celsius. On Titania, the largest moon of Uranus, the average temperature is 78 degrees Celsius. And here, as we see, no atmosphere has formed, and basically, it's just such a hot moon. Next is the planet Neptune. The average temperature on it has settled at minus 38 degrees Celsius, and now it's moon Triton, and it's also turned greenish, something similar to Uranus. The surface is visible right here. The average temperature on it is minus 126 degrees Celsius. Well, it's cold here. If we hide the atmosphere and clouds, we see a completely icy world, and only here at the poles does everything look different. On this pole, there's a mark like this, as if something was happening here. Well, as we see, Neptune is currently in the green zone, but almost at the farthest point from the star. Let's see what's going on with Pluto. This is what it looks like, losing its matter. We see a dense atmosphere, and apparently, due to its low mass, this atmosphere is simply escaping into space. The average temperature is minus 96 degrees Celsius, but as we saw, Pluto is quite far from the star, even if it's in the green zone. If we hide the atmosphere and clouds, Pluto's surface is basically unchanged. I don't see anything new at the poles either. And this is how the red giant sun looks from near Pluto. Right now, you see the distant dwarf planet Eris with a surface temperature of minus 51 degrees, but at the equator, it's around 37 degrees Celsius. And looking at the other dwarf planets, I didn't see anything particularly special there. The temperature just increased, and no atmosphere formed there. When the core temperature reaches 100 million Kelvin, a helium flash will occur, and a thermonuclear helium-burning reaction involving carbon will begin. The Sun, having received a new energy source, will decrease in size. This will happen in about 6.75 billion years, in an era when the Sun's core will suddenly trigger helium burning. This will temporarily stabilize the Sun and create a relative equilibrium in the solar system, but not for long. Much more dramatic changes await the solar system ahead. You will see this in the second part of the video, which will be released in a week.